Good evening, everyone. You are tuned into Boise State Physics First Friday Astronomy. My name is Heidi Wu, and I'm the new assistant professor at Boise State Physics, and I'm probably the newest astronomer in Boise, so I'm very excited to host this event today. Before we get started, I'd like to briefly go through a few technical details. So we have talks on first Friday of every month, not just during school years, every month. So we have 12 talks in a year. So in December, next month, we will have Dr. Kathy Olken from Southwest Research Institute telling us about NASA's Lucy mission, 1 spacecraft, 7 Trojan asteroids, and 12 years. And during this talk, if you like to ask questions, please use the chat feature on YouTube. I like to quickly show you how to do it. So on the right hand side, you can type your questions here, and you have to sign in to do that. And we will be looking at I will be looking at the monitoring the chat and answering questions. Does anybody else hear a bad echo? So please do let us know if you keep hearing that, and I'm sorry about the technical difficulty. So today, I am very, very excited to be introducing Dr. Barbara Ryden from The Ohio State University. Dr. Ryden received her bachelor's degree from Northwestern University and a PhD from Princeton University. And her research focused on galaxies and large-scale structure in the universe, which is also very close to my heart. And in addition to be a very successful cosmologist, Dr. Ryden is also a famous author of several very popular textbooks. One of her books, Introduction to Cosmology, won the Chambliss Astronomical Writing Award of the American Astronomical Society. It is also my favorite book, not just my favorite textbook, but my favorite book. Without further ado, let's welcome Dr. Ryden.
Well, thank you, Professor Wu, for that, frankly, quite flattering introduction. I hope I can live up to it. Also, before I start my presentation, I want to give a slight explanation of the title of my talk, A Practical Guide to Time Travel. Now, if you think that you'll be walking away from this talk with a complete set of blueprints to build your own time machine, that's not exactly what I meant. When I talk about practical time travel, what I mean is, does time travel obey the laws of physics? So if it's okay with the laws of physics to travel through time, then even if it costs hundreds of trillions of dollars, then I regard it as practical. So since there's not too much exciting about staring at me talking, I'm going to bring up a PowerPoint presentation, lots of pretty pictures for you to look at. And in particular, if like me, you're a big Doctor Who fan, you have a mental image of what it means to travel through time. You hop into your time machine, a TARDIS in the case of the Doctor, and you turn a few knobs, pull some levers, and there are a few minutes of whoop, 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 whoop noises, your time machine disappears from one spot and then reappears in another. So, excuse me while I fiddle with the display here. Now, if you take away all of the fancy whoop whoop noises, what time travel into the future means is, while only a few minutes perhaps pass for you personally, everything outside of your time machine travels perhaps hundreds, perhaps thousands of years into the future. So time travel into the future simply means that your clock, or more broadly, the flow of time that you experience, is much slower than the flow of time for everyone around you. So you experience a few minutes while everyone else experiences hundreds or thousands of years. So time travel into the future sounds interesting, sounds fun, but does it conform to the laws of physics as we know them? Well, there was this guy called Einstein. You may have heard of him. In the early 20th century, he put forward his theory of relativity, both special relativity, the special case in which gravity doesn't exist, which he then expanded to his general theory of relativity, which deals with the general case in which gravity exists, and which, in the view of Einstein, results in the warping of space and the distortion of time. Now, Einstein, of course, had many, many brilliant ideas, but the one I want to focus on right now is his idea about how clocks measure time. So he realized that if you had a clock and you accelerated it, say you attached a large rocket to it and sped it up through space, then that clock would run more slowly than a clock that's simply moving at a constant speed. Now, the fact that the clock runs more slowly, that's not a defect in the clock. Accelerating it doesn't make the machinery break down. What he's saying is that time actually runs more slowly for an accelerated clock or an accelerated person. So if I could attach a rocket to myself and accelerate myself to higher and higher and higher and higher speeds, then I will age a few minutes, while the outside universe will age by years, centuries, perhaps millennia. It depends on how greatly I can accelerate myself. So a practical time machine doesn't look like the Doctor's TARDIS. It doesn't look like this cartoon adaptation of H.G. Wells's Time Machine, but it could look like a rocket ship, anything that will accelerate you through space to higher and higher speeds. So I'm going to give you an example of how very great acceleration can cause time to run more slowly for you and for this surrounding universe. And so for my example, I'm going to call upon Waldo and Wanda, the amazing time-traveling warthogs. I know, you weren't expecting warthogs in an astronomy lecture, certainly not one about time travel. I'm going to be using Waldo and Wanda, the warthogs, because I want a sentient being that is really, really tough. And warthogs, let me tell you, warthogs are really tough. So Waldo and Wanda have decided they want to do an experiment traveling through time. They have a very large rocket ship with a very potent fuel source. And so they flip a coin. I don't know how warthogs can flip coins without having fingers, but they decide somehow who's going to travel on the spaceship and who's going to stay at home. As it turns out, Waldo is the one who climbs on board the spaceship, ready to blast off, while Wanda stays behind and waves goodbye to Waldo. Now, I told you this was a spaceship with a really, really, really powerful rocket engine. And so when Waldo lights the engine and starts taking off into space, he accelerates away from the Earth in whatever direction he's chosen at 10 G. G here is the usual scientific symbol for the acceleration you experience just by standing here at the surface of the Earth. So if you drop, for instance, a rock from a tall tower, it will start at rest and then fall faster and faster and faster. So every second of time, its speed increases by 9.8 meters per second. So after 1 second of falling, it's going almost 10 meters per second. It's going as fast as a sprinter. After 2 seconds, it's going twice as fast, nearly 20 meters per second, much faster than someone can run, and so on and so forth. So I'm going to specify that Waldo is accelerating not at the mere 9.8 meters per second that you experience in free fall near the Earth, but he's going to have an acceleration 10 times that. This is why we need a tough warthog. As Randall Munroe reminds us in his really great cartoon XKCD, acceleration is bad for the human body. Imagine you're in space instead of Waldo, and you attach a rocket to your head, accelerating you downward. This is bad because the blood all accumulates in your head, and at as little as twice G, the acceleration at the surface, this, let's just say, has bad consequences for your health. Not so bad accelerating upward or backward. Accelerating forward. Imagine you're lying on your back on a couch and the couch is being accelerated forward. Yeah, it's not so bad. Your eyeballs are unhappy. Oops. And maybe if you're in a nice comfy couch, you can survive 20 Gs in that position. However, you're just going to be pinned to the couch and you can't keep this up indefinitely. So 10 G, even if you're a tough warthog, that's about the best you can do by way of acceleration. That's the maximum acceleration that's consistent with, not squashing you eventually. So Waldo's tough. He can stand 10 times the usual acceleration at the Earth's surface. It means he weighs 10 times as much, which makes it difficult to move around his spaceship. But he's tough. He keeps this up for 6 months, half a year. And this is time as measured by his own clock and his own calendar that he's taken along with him on his spaceship ride. By the time he's kept this up for 6 months, he's traveling at something like 99.99% the speed of light. He's going really fast, like a warthog out of hell. He realizes, oh yeah, if I want to return to Earth, I'd better start accelerating in the opposite direction so that instead of speeding up, I slow down. So as seen here in the bottom sketch, Waldo turns his spaceship around 180 degrees and accelerates in the direction towards Earth at 10 G for 6 more months. So according to Waldo, at this point in time, he's been spending an entire year under this very high, very uncomfortable acceleration. And when he stops, he's now at rest relative to the Earth. He looks back in the Earth's direction and he says, oh, wow, I'm now 16.7 light years away from the Earth. That's about as far away as the star Altair. So if he's chosen the right direction, he can stop, check out the Altairean planetary system, but let's face it, he wants to go home. There's no place like home, right? So what does he do? Again, he has this ultra powerful rocket ship and some arbitrarily large supply of fuel. Again, my definition of practical is a little stretched here, but suppose he has enough rocket fuel to accelerate back towards Earth. That's 10 G, 10 times the acceleration at the Earth's surface for 6 months. And then he's going 99.99% the speed of light towards the Earth. He does not want to slam into the Earth at highly relativistic speeds. This would not be good. So he needs to slow down once more, turns his spaceship around 180 degrees, and fires the rockets. He's still accelerating at 10 Gs, but now away from the Earth, and 6 more months. So to summarize, from Waldo's viewpoint, he's been spending 2 entire years, according to his own clock, accelerating at a really terrific rate. So when he gets back to Earth, by Waldo's clock, 2 years have passed. However, by Wanda's clock, she's been staying behind on the Earth, and her clock goes around and around and around. She flips the page on her calendar over and over and over, and by Wanda's clock, 34 years have passed. So I've been careful to use as large an acceleration as is compatible with warthog physiology. And you can see there's a considerable difference in the rate of time as experienced by Waldo, very slow, and that experienced by Wanda, very rapid. So yes, the laws of physics, according to Albert Einstein, not only permit time travel into the future, but actually demand time travel into the future. An accelerated clock runs more slowly than a clock that isn't accelerated. And all of us at all times are experiencing acceleration. We are on a planet that's being accelerated as it goes around the sun. The sun is being accelerated as it goes around the center of our galaxy. And so every one of us has a clock running at a slightly different rate. Most of the time, the difference in acceleration is too tiny to measure. And it takes something really heroic, like Waldo's 2 years of constant acceleration, to make a significant difference. So now consider Waldo's point of view. He wanted to travel into the future, and he's done it. He had to spend 2 years very uncomfortably instead of spending a few minutes looking at flashing lights and hearing whoop whoop noises, but he's done it. Unfortunately, you should be careful what you ask for. 34 years, the time that's elapsed by Wanda's clock, is longer than the lifespan of a warthog. So Waldo has done what he wanted. He's traveled into the future, but alas, his best buddy Wanda has now passed away. So the idea that an accelerated traveler can travel forward in time as well as out and back in space is really a staple of classic science fiction novels. So travel into the future using a highly accelerated journey is quite common. Here I've just shown a few classic science fiction novels. Time for the Stars by Robert A. Heinlein from the 1950s features a pair of twins. One goes out and back on an accelerated voyage, the other one stays at home. And when the accelerated twin returns, I believe he ends up marrying his great-great-grandniece, or maybe it's just a single great-grandniece. But as you can see, traveling forward in time can result in some rather awkward social situations. The Forever War, famous science fiction novel by Joe Haldeman, is about a soldier. He signs up for a 4-year stint. However, it's a 4-year stint traveling at high acceleration, hundreds of light years away and back in the course of an interstellar war. He comes back to Earth. 4 years have elapsed for him, but on Earth, centuries have passed. He comes back and discovers he can no longer speak the language, that cultural shifts means that everybody stares at him really, really strangely. Who is this very odd person from the past? And A World Out of Time by Larry Niven, another classic from the 1970s, is an extreme example of the genre. Here, a space traveler hijacks a spaceship, goes to the center of our galaxy and back, very strong accelerations. He comes back billions of years later. The sun has become a red giant. The Earth has been moved so that it's now a moon of Jupiter, and human society is completely changed beyond all recognition. So in science fiction, the very real result of Einstein, that an accelerated clock, including your own biological clock, runs more slowly, has been explored by science fictional writers to explore themes of alienation. You cannot go home again, especially after billions of years. Things just change beyond all recognition. Now, traveling into the future is interesting, but as Waldo discovered, if you travel into the future and you don't like what you find there, well, are you stuck? Can you travel backward in time? Can you travel into the past? Let's face it, all of us have at times desired that we could go back in time to change something, even if it's only, oh God, I hit reply all instead of reply. So is going backward in time compatible with the laws of physics as we know them? Well, again, here we can go back and look at the relativity theory of Einstein. As we've seen, time travel into the future is not only permitted by Einstein's theory of relativity, it's actually required. Everybody is accelerated at a slightly different rate in the universe, so everybody experiences time running at a slightly different rate. Some of us have clocks running a little more slowly, some of us have clocks running a little more rapidly, but always into the future. There is, well, I want to call it a loophole, but it's actually a wormhole in Einstein's theory of general relativity that permits travel into the past. Einstein's theory of general relativity, as I mentioned earlier, deals with the general case in which gravity exists. Newton told us gravity is a force acting between two massive objects. Einstein says, well, no, gravity is the distortion of space and time in the vicinity of something massive or something that has lots of energy. Remember, E equals mc squared. Energy and mass are interchangeable. Now, a famous extreme distortion of space as the result of a concentration of mass and energy is a black hole. And on the left of the screen that I'm showing now, it's the usual cartoon display of a black hole. It is intended to display how space, here represented as a two-dimensional rubber sheet, becomes very distorted so that you get a dimple in space close to a very dense, very compressed black hole. So a black hole we know exists. We can see their effects on space-time. However, there's something even more exotic and more strange than a black hole called a wormhole. Now, if you've read the novel Contact or seen the movie adaptation of that science fiction book by Carl Sagan, it's based on the assumption that there's a wormhole, a tunnel between 2 points in space, going from the solar system to a point near the star Vega. Now, from the Earth to Vega, through ordinary everyday space, is 25 light years, so takes a while to get there. However, notice the wormhole is a tunnel that permits you to take a different path. And in this case, as we see, the wormhole is a shortcut. The distance through this tunnel in space, through this wormhole, is shorter than 25 light years. So wormholes, it was realized in the first half of the 20th century, are a mathematically valid solution of Einstein's equations. And the term wormhole, it isn't kind of this jocular slang. It is, in fact, the technical term for a tunnel through space of this kind. The word wormhole was actually coined by a famous physicist, John Archibald Wheeler, in 1956. He's also the physicist who popularized the phrase black hole. So he's a man with a real turn for a catchy phrase. And Well, at the bottom, you can read Wheeler's own words, a flux of lines of force through what topologists would call, quote, a handle of the multiply connected space. Yeah, topologists really do talk like that. And what physicists might perhaps be excused for more vividly terming a wormhole. So, yeah, we'll let topologists use whatever language they choose. It's their right, but let's be physicists for a while and call this tunnel through space-time a wormhole. So a wormhole can provide a shortcut through space. So yeah, through ordinary space, you go from Earth to Vega, you have to trudge 25 light years to get there. The distance through the wormhole on the left, though, is much shorter. It looks like about 5 light years, at least according to this drawing. The point is, however, sorry about that, minor glitch, the effective result is you can travel faster than light. Instead of taking 25 years to get from Earth to Vega, light can get there in 5 years because it knows a shortcut. Now, I should point out, truth in advertising once more, that the distance through the wormhole doesn't have to be shorter than the distance through ordinary space. Some wormholes can be long cuts. So wormholes mathematically permitted solutions to Einstein's equations about the distortion of space. They can be either shorter or longer than the distance through ordinary space between the two ends or mouths of the wormhole. And if you're lucky enough to find a wormhole between point A and point B, if it's a shortcut, you can effectively travel faster than light. And also, it lets you cheat in a game of tag. Now, once again, trying to be strictly honest here, Einstein's equations permit the existence of wormholes. We have absolutely no idea how to make them. People speculate, oh, we need this special kind of negative energy to hold the wormhole open and keep it from pinching down, but practically we have no idea how to make them. Cats, of course, cats are a special case. They can distort space and time to their will. Humans, however, have no idea how to make wormholes. So let's suppose that there exists a wormhole somewhere in our universe. We don't know how to make them, but perhaps there were wormholes kind of baked into space and time from the beginning. One of the fun attributes of a wormhole is that you can take the two ends of the wormhole, they're called the mouths of the wormhole, and you can move them relative to each other through ordinary space without lengthening the wormhole. This is kind of a weird thing to do. This diagram, I stole it from Kip Thorne's really great book. And it shows a wormhole. On the left, the wormhole has its mouth located at point C, but now we slide the wormhole from right to left so that one mouth of the wormhole, the bottom mouth, is no longer at point C, it's at point B. And then the final panel of this 3-panel cartoon on the right, we've slided the bottom mouth of the wormhole still further to the left so that it's now connecting to point A in space. Notice all this time, the distance through the wormhole remains constant. This is kind of an interesting attribute of wormholes. You can move the mouths around in ordinary space, but the distance through the wormhole, through the tunnel, remains constant. And this permits travel into the past, okay? We're gonna see how this can happen by bringing back, once again, Waldo and Wanda, the amazing time-traveling warthogs. Now, Waldo, taking the same trip as before, really fast acceleration, 10 times g, 6 months away, turns around, accelerates 6 months back. He's now at rest with respect to the Earth. way the hell and gone near Altair. 6 months accelerating back towards the Earth, swivels his spaceship around and accelerates back towards Altair so that when he gets back to the Earth, he's finally at rest with respect to the Earth instead of crash landing at many times the speed of light. So exactly the same journey as before, but now Waldo and Wanda have a wormhole. Through the wormhole, between one mouth and the other, it's about a yard long, a meter if you prefer metric units. Waldo takes one mouth of the wormhole, loads it aboard his spaceship. Wanda keeps the other end of the wormhole at home. So it just stays at Earth. So this is the case where Waldo's end of the wormhole is being moved relative to Wanda's end through ordinary space, but through the wormhole, it's still only a yard long. So all during this trip, even though Waldo is traveling 16.7 light years away, Waldo and Wanda can chat through the wormhole. They agree on what time it is. If Waldo runs out of warthog chow, Wanda can shovel some in. It's only a yard through the wormhole. And all of this time, Waldo and Wanda having a nice chat, a 2-year-long chat, and they agree on what time it is. After all, since the two mouths of the wormhole are at rest relative to each other as measured through the wormhole, the two ends aren't being accelerated relative to each other. So the clocks of Waldo and Wanda at the two ends of the wormhole are running at exactly the same rate. So let's suppose Waldo leaves Earth right now. Bing, this very instant, he blasts off from the Boise State University campus, November 6th in the year 2020, and spends 2 years, according to his own clock, traveling out and back. He returns to Earth on November 6th, 2022, by his own accelerated clock. Before Waldo leaves his spaceship, he shouts through the wormhole, "Yo, Wanda, what day is it?" Well, since Wanda, through the wormhole, agrees with Waldo what time it is, Wanda says, yeah, at my end of the wormhole, it's November 6th, 2022, according to Wanda's clock, an earthbound clock. Okay, Waldo's ready to jump out of his spaceship, which has landed on the Earth. He opens up the hatch, leaps out, asks a passing warthog, excuse me, what day is it? I'm sure the passing warthog is a bit nonplussed. Here's this strange guy who's just leapt out of a spaceship wanting to know what time it is, but the passerby looks at whatever the future equivalent of a smartphone is and says, it's November 6th, 2054. 32 years later. So let's stop and contemplate what's going on here. The difficulty with talking about time travel is that the verb tenses get a little bit confused. Time travel is, was, is going to have been confusing. So let's look in summary to what's happened to that wormhole. The wormhole is in fact now a time machine. The ends of the wormhole, the mouth of the wormhole that Waldo took with him on his accelerated journey is now in the year 2054, according to Earth clocks. The end that stayed at home with Wanda is in the year 2022, according to Earth clocks again. So now Waldo has an escape hatch or an escape wormhole. If he doesn't like the year 2054, in part because his good friend Wanda is dead, he can always crawl back through the wormhole to the other end where it's still 2022 and good old Wanda is still alive. So now you have a way to travel between two times. Notice that both ends of the wormhole are now at rest with respect to each other. They're both now on Earth. And so they will continue to move into the future at very nearly the same rate, but one end of the wormhole will be 32 years ahead of the other end of the wormhole. there are certain difficulties. If Waldo decides he doesn't like the year 2054 and jumps through the wormhole 32 years back into the past, he could bring along 32 years of winning lottery numbers, 32 years of the outcomes of sporting events, 32 years of technological innovations that he could pass off as his own invention. And thus, we are forced to conclude that the absence of billionaire warthogs is definitely a sign that warthogs haven't mastered time travel. And in fact, yeah, that's one of the practical reasons why we think you can't travel backward in time, because there's no evidence that anybody has traveled from the future to now with any sort of advanced information. The reason why lotteries work is that, oh yeah, nobody knows in advance what the lottery number is going to be, unless, of course, they rig the lottery in an ordinary, non-time travel sort of way. There is, however, one counter-argument. Professor Rich Scott at Princeton University, who was one of my professors when I was there at graduate school, maintains with a remarkably straight face that the reason the Titanic sank wasn't because it hit an iceberg, but rather because it was overloaded with time travelers who had gone backward in time because they wanted to see the sinking of the Titanic. Okay, he's able to keep a straight face when he says that, but I always burst out laughing. I think this is a very funny joke. So, the main problem with time travel into the past is not that it enables warthogs to become billionaires or causes the sinking of the Titanic, but that it causes logical paradoxes. The most famous of these is called the grandmother paradox, sometimes the grandfather paradox. But I want to express it in terms of warthogs once again. I'm on a warthog roll. In the year 2054, Wanda has a grandson by the name of Wallace. It's a little known fact that warthogs all have names starting with a W. Wanda's grandson Wallace walks up to one end of the wormhole. Remember, one end of the wormhole is in the year 2054. The other end is back in the year 2022. Wallace says, oh, this is an interesting hole in space. I wonder where it leads to. And young Wallace, being a rather impetuous young warthog, leaps through the wormhole, comes out the other end near 2022. Unfortunately, he collides with his grandmother Wanda at very high speeds, and in the resulting terrible catastrophe, poor Wanda is killed. The problem, and the reason why the paradox arises, is that in 2022, poor dead Wanda had not yet had her first litter of warthog piglets. So poor Wanda, killed in this tragic accident, has no descendants. So yeah, once again, time travel is confusing. I will have said the same thing a few months from now. Let's look at the logic of this. Okay, Wanda is killed in an accident by her grandson. As a result of being killed at a tragically early age, Wanda has no children and therefore no grandchildren. However, if Wanda has no grandchildren, in particular, she does not have a grandson named Wallace, and therefore she's not killed by that grandson Wallace. But since she hasn't been killed, she grows up and meets the warthog husband of her dreams and has lots of children and grandchildren. But the fact that she now has grandchildren means, in particular, she has a grandson named Wallace, who is able to travel back in time to kill her before she gives birth to any children, and therefore she has no grandchildren. And yeah, you have this logical paradox in which Wanda simultaneously has and does not have grandchildren. Now, logical paradoxes, don't know about you, they make my brain explode. And many eminent physicists believe that in a well-regulated universe, you should not have paradoxes of this kind. In particular, Stephen Hawking, while he was still living, put forward what he proposed as the chronology protection conjecture. That is, paradoxes cannot exist in a well-regulated universe. Therefore, there must be some law of physics. We haven't discovered it yet, but there must be some law of physics that prevents time travel into the past. Because if you could travel into the past, then you could kill your grandparents and therefore you would disappear in a puff of logic. But in that case, if you didn't exist, you would not be able to go back in time and kill your grandparents. And I could just keep repeating this over and over and over, the cycle of paradoxes for minutes on end. However, I want to wind up here and say, yes, time travel into the future is possible. And in fact, it's mandatory, not just in the trivial sense that we're all moving forward in time at a rate of 1 day per day, but in the more interesting sense that it is physically possible for one person's time to run very, very slowly compared to the time experienced by other people. This is what we mean by time travel into the future. If these mathematically permissible structures called wormholes exist, then, according to Einstein, time travel into the past should be permissible. However, since time travel into the past causes paradoxes, and we really don't want a universe with paradoxes of this kind, it is conjectured by people much smarter than I am that there has to be somewhere in the laws of physics, some law that forbids us to travel backward in time and mess around with the past. So if you could go back in time, think about it. If you could go back in time and talk to your younger self, I think it would be a good idea to say, just stay away from time travel, dude. It's really dangerous, not just for you, but also for your dear grandmother. And I'm winding up a little early here so that you can have time to pose questions into the chat window that I can answer for you. So thanks a lot. I was very pleased to be able to come here and speak with you, even though it's virtual. And I'm sorry, I have a problem because I'm getting a software update right now. Let's see if I can come back here. And see what questions you have.
This is really amazing. Thank you so much, Barbara. And yeah, this is so much fun. So do we have questions on the Zoom here or from the audience? Please do put your questions in the chat. Actually, the audience will be a few minutes delayed on YouTube. So I guess we can ask questions here. So if I may ask, what exactly is this conjecture to prohibit paradoxes or?
Well, the wonderful thing about a conjecture, of course, is that it can be extremely vague. There must exist some sort of law. We haven't found it yet, but a law that would forbid us to travel back into the past and mess around with it in ways that would prevent us from going back in the past in the first place. Like many people, I am fascinated by the idea of the logical paradox, but I don't want to encounter them in the real universe.
Alexia, would you like to ask a question?
Hi, is it okay if I talk?
Sure, absolutely.
Yeah.
So can you explain what a wormhole is physically? From what I understand, a black hole is like the bending of space. I'm not exactly sure, but how is that different for a wormhole?
Oh, well, in the picture that I showed on screen, the wormhole I described as a dimple. But if you took two black holes and if you could sew them together, so going into one black hole and then emerging from the other, if you can imagine that. The problem, of course, is that we're talking about the distortion of a four-dimensional space-time, and I'm trying to describe it using a two-dimensional cartoon projected onto a screen. So a lot of general relativity, if you're actually doing general relativity as a scientist, is really horrible, horrendous calculations. And anything that you see at a more popular science level, anything qualitative, is just a cartoon approximation of what's going on. I realize that's not a very satisfying answer, but if I just threw up a screen full of calculations from Einstein's field equation of space-time curvature, I don't think that would be very helpful either.
Thank you.
You're welcome.
So we have a question here on Zoom. Nuha, would you like to ask your question?
Sure. So my question basically is just, how do you mathematically prove that wormholes exist? Like, how do you quantify that kind of concept?
Oh, well, again, the mathematical relations, Einstein's famous field equation of general relativity, are in general very complicated. You have to describe the curvature of space everywhere, and you have to do it for all time. So it's a four-dimensional problem. Now, finding exact solutions for those very complicated equations is difficult. The solution for a black hole, the famous Schwarzschild solution by Carl Schwarzschild in 1916, was a very early example. And Einstein and a lot of other people were trying to find other solutions. So saying it's a mathematically valid solution to Einstein's equations describing space-time curvature says, yes, you can curve space and distort time in this way. And it also tells you what sort of mass and energy content you have to produce that particular distortion or stretching or puncture or dimple or wormhole in space.
Oh, okay. Thank you.
We have a question from Tiffany Watkins. She says, when I think about wormholes, I think about it as a black hole on each end creating it. So then can we really travel through with those gravitational fields on each end?
Ah, yes, you've kind of put your finger on it, because the extreme distortions of space-time near a black hole have the unfortunate side effect of, I love this word, spaghettification. You have experienced tidal forces so great that you are literally stretched out like a long string of spaghetti. This is not good. And so is it actually possible, even if you could build a wormhole, to pass through it without being shredded by tides? Again, another minor detail. This could be how, this could be how the space-time protects itself, the chronology protection conjecture. Maybe it's just impossible for any physical object to pass through a wormhole.
Wow.
Assuming, of course, that wormholes actually physically exist, as opposed to being merely a mathematically possible solution of the equations.
Right. Yes. And we have another question from Jordan Akeley. He says, I know it is very sci-fi, but would a time police both allow for time travel into the past and allow for a paradox-free universe?
Time police. Yeah, it's very sci-fi, isn't it? And again, a lot of conjectures. One conjecture is if somebody goes back in time and tries to change things, then the universe somehow repairs itself. Perhaps not necessarily, time police made out of stalwart science fictional heroes and heroines, but maybe the universe is kind of self-repairing and it patches up all these paradoxes. Science fictional, speculative. Another speculation is that, yes, it's possible to go back in time, but every time someone travels into the past and makes a change there, the universe splits in two. For instance, when Wallace goes back in time to kill his grandmother, the universe splits in two. In one of those universes, poor Wanda is killed in this horrible accident by a crazed warthog who just appears out of a wormhole. He asserts that he's from the future. He asserts that he's Wanda's grandson, but everybody says, oh, poo, poo, poo. We know Wanda doesn't have any grandchildren, poor thing. And then in the other universe, Wanda lives to a ripe old age, has children and grandchildren. Her grandson, Waldo, disappears into a wormhole and is never heard from again. In each of those two universes, there are no paradoxes. However, it's a really, really freaking weird concept. Just because somebody goes back in time, all of a sudden, where you had one universe before, you now have two universes. And in each of those two universes, if somebody goes back in time and does something, they too will split in two. So you have these propagating universes, which is probably even a more freakish concept than being able to go back in time and simultaneously kill and not kill your grandmother. It gets really, really weird, really fast when you think about traveling backward in time. Notice traveling forward in time, yeah, no problems. You can travel forward in time all you want, but you can't go home again. You can't go back to where you started. That sounds accidentally philosophical, doesn't it?
And we have one question from Brian Shakespeare. He says, if we can't travel back in time due to some law we haven't discovered, couldn't the opposite be true? That we haven't discovered a law that would allow it?
Yes. Oh, I was talking about some conjectures. Every time somebody goes into the past, you split a universe into two separate universes. And it could be that the solution to the apparent paradoxes of time travel into the past is something even weirder that we haven't thought of yet.
And one more question from JLCOP. And the question is, has anyone found any evidence of wormholes?
No.
Got it.
Short answer, no, nobody's found any evidence of wormholes. However, physicists, like everyone else, like a good sit down and speculation period every now and then. You have to admit, thinking about this stuff is awfully fun.
Yeah. So Justin, on the Zoom call, would you like to say your question?
Hi, sure thing. First of all, thank you very much for this presentation. I've been reading a little bit about something that I think is related, and I just want to see how related they are. And those are closed timelike curves. Are CTCs kind of similar to wormholes, or are they just something that you can sort of diagram on a Lorentzian manifold or Minkowski space, but they're really not, they don't have the sort of application that we see for a wormhole?
Closed time-like curves. Now you are exposing very, I was supposed to say very blatantly the limits of my knowledge about general relativity. So again, closed time-like curves are something mathematical that you can write down in the context of Einstein's theory, but whether they have any sort of quote unquote real application, don't know. There's a lot.
So they're really a mathematical exercise that, I mean, CTCs.
I would say so, but you really need to bring in an honest to God relativist for one of your first Fridays.
Thank you very much. Thank you.
You're welcome.
So there's an interesting comments on YouTube. Brian Shakespeare says, "My thinking is that humans evolved to recognize forward time travel. If we would have evolved differently, it is possible that backward time travel will make complete sense as well." And are there other questions here on Zoom or on YouTube? So Jordan asked, in the beginning, you mentioned a negative gravitational force that would go about keeping a wormhole open like exotic matter. Could you elaborate?
Oh, yes. I was talking earlier about wormholes, and one of the rather inconvenient properties of wormholes is that if you make one, it's been shown, again, using Einstein's theory, that they tend to pinch themselves off. So if you have a wormhole, there's this natural tendency for it to narrow at the middle and pinch off, so you get two disconnected black holes in very different regions of the universe. And so you have to keep the wormhole open somehow. And there's a type of, again, not yet discovered, still highly hypothetical, exotic matter with negative energy density that holds the wormhole open long enough that you can pass through. Of course, you might be badly spaghettified by the extreme curvature of space-time passing through, but in theory, once again, even keeping a wormhole open long enough to pass through requires this kind of exotic negative density energy that, once again, we've never seen anywhere in the real universe.
Yeah, it looks like we don't have more questions on YouTube. And so once again, thank you so much, Barbara. This is really a treat for the entire city, and perhaps we have audience from other parts of the country as well. And thank you again.
Well, I had a great time. I only hope that sometime in the future I can come physically to Boise and meet all of you in person.
And thank you. And with that, and let's conclude today's First Friday Astronomy. and see you next month.